Hey guys, welcome back to NPTutoring. Today we're going to do a vector analysis problem from this textbook. It's Classical Mechanics by Kibble and Berkshire. The problem states, an aircraft is to fly to a destination 800 kilometers due north of its starting point. Its airspeed is 800 kilometers per hour. The wind is from the east at a speed of 30 meters per second. On what compass heading should the pilot fly? How long will the flight take? If the wind speed increases to 50 meters per second and the wind backs to the northeast, but no allowance is made for this change, how far from the destination will the aircraft be at its expected arrival time? So there's a bunch of information in this question, and let's go ahead and tackle it piece by piece. Here's the first part. Let's go ahead and call this green dot the starting point, this red one the destination. The space between them is 800 kilometers. And here's the compass with north, south, east, and west. And notice that the starting point, notice that the destination is north of the starting point. Here's an arrow. This arrow represents a vector. And this vector will be the aircraft, which is going at 800 kilometers per hour. And this vector will be the wind, which is 30 meters per second. So first thing we'll do is let's go ahead and change into proper units because the aircraft is in kilometers per hour, the wind is in meters per second. When we change everything, the aircraft is actually going 222 meters per second, the wind is still 30 meters per second, and the distance is 800 times 10 to the third meters between the starting point and the destination. Next, let's go ahead and break these down into components. Before we do that, notice that the aircraft is purely in the y direction, and notice that the wind is purely in the x direction. And that's made easier to visualize if we were to introduce this two-dimensional coordinate system with the y-axis and the x-axis. So breaking these down to components, the wind, the x component for the wind, will be 30 cosine 180, and then the y component will be 30 sine 180. Now, you may ask where this 180 came from. So, with respect to the x-axis going counterclockwise, the wind is at 180 degrees counterclockwise from the x direction, or the x-axis, I mean. So that's where that 180 comes from. Likewise, this 90, representing the aircraft, is 90 degrees from the x direction counterclockwise. And the components for the aircraft is 222 cosine 90, for the x component, and then the y component is 222 sine 90. When we go ahead and evaluate this, we get minus 30 for the x and 0 for the y for the wind, and then we get 0 for the x and then 222 for the y for the aircraft. And when we go and add these to get the resultant vector, we get minus 30 for the x component and 222 for the y component. Now, if we were to add these vectors visually, here's what it would look like. Here's the aircraft, here's the wind, and here's the resultant vector. And this makes sense because in component form, notice we have a negative value for x, positive value for y. This vector, the resultant vector, is in the negative x direction, and then it's pointing in the positive y direction. Now, to help figure out which compass heading the pilot should fly, let's go ahead and compute the angle, and the angle being this angle right here, the angle between the resultant vector and the y-axis. To help doing so, let's go ahead and reintroduce the two original vectors, the aircraft and then the wind. Now let's place all these arrows or vectors by a right triangle. Now, this right triangle shown here has 30 on this side and then 222 on this side. Again, this triangle represents the vectors. So the 30 is the wind vector, the 222 is the aircraft vector, and we're trying to figure out this angle we'll call theta. So to figure out that angle, we're going to recall this famous saying, or this common saying in trigonometry called SOHCAHTOA, which is sine opposite over hypotenuse, that's the S, opposite is O, and hypotenuse is H. Cosine is C, adjacent over hypotenuse, which is this A. Then tangent is opposite over adjacent. Given this right triangle, we have this hypotenuse right here. We have this adjacent side by the 222, and then we have this opposite side represented by the 30. So since we have opposite and adjacent side, we're going to go ahead and use tangent. And to solve for this angle, we have tangent of the angle theta equals 30 over 22, or 222. And solving for that angle, we have the theta equals tangent inverse of 30 over 222, which is 7.7 degrees. So theta is 7.7 degrees. Now, going back to this x and y axis, we actually need this vector. Why? Because this is 7.7 degrees this way, which is west of north. So we computed this angle, but the question is asking on what compass heading should the pilot fly. So to help compensate from the wind, which is coming in from the east, the pilot should fly in this direction, which is 7.7 degrees east of north. So the pilot or the aircraft should fly on a compass heading 7.7 degrees east of north. If the pilot flies in this direction, the wind will blow it back into a straight path, leading it to the destination. Now the next question is, how long will this flight take? So to answer this, let's first solve for this hypotenuse. Now, this hypotenuse is the distance. It has nothing to do with the vectors that we calculated earlier. So we're given this angle, or not this angle, this side length, which is 800 times 10 to the third meters. It's the distance between the starting point and the destination. We're given this angle, which is 7.7 degrees. Now first we want to solve for this hypotenuse, and then using this distance, we can use the distance and time formula to solve for the time. So again, we're going to use SOHCAHTOA. This time we have the hypotenuse, and then we have the adjacent side. So we're going to go ahead and use cosine. Cosine of 7.7 equals 800 times 10 to the third over x. Solving for x, we have 800, or x equals 807 times 10 to the third meters. Now we're going to use the distance formula to solve for time. The distance formula is actually derived from this formula. Remember, velocity equals distance over time. That's why velocity in common units, it's measured by meters, distance, over seconds, which is time. Solving for time, time equals distance over velocity. Plugging in the numbers, we have 807 times 10 to the third over 222. And calculating that, we get time equals 3,635 seconds, which we divide by 60, which would be 60.6 minutes. So the flight will take 60.6 minutes when following the 7.7 degrees east of north heading. Now for the second part of the question. If the wind speed increases to 50 meters per second and the wind backs to the northeast, but no allowance is made for this change, how far from the destination will the aircraft be at its expected arrival time? So going back to the system, we have the starting point, we have the destination. We have this vector which represents the direction the plane is going originally. Remember, no allowance is made for this change, so we're going to go back to this vector. Here's the wind coming in from the northeast. The aircraft is going 222 meters per second originally, and then the wind is coming in from the northeast at 50 meters per second. Again, let's break this down into components. For the wind, we get minus 50 because it's coming in towards the negative x direction, cosine 45 for the x component, and then minus 50, again because it's going in the negative y direction, sine 45. So the reason we get 45 is, looking at this compass, between north and east, there's a 90-degree distance. Northeast is right in between north and east, obviously. So half of 90 is 45, and that's where we get this 45 degrees from. And We also have this theta that we calculated originally, which is 7.7 degrees. That's going to come in handy when getting the components for the aircraft. So for the aircraft, the x component is 222 cosine 82.3, and the y component is 222 sine 82.3. Now you may ask where this 82.3 came from. So with all the calculations thus far, we've been calculating counterclockwise degrees with respect to the x-axis. The 7.7 is with respect to this y-axis going east of north. So to get this distance, or this angle, we're going to subtract that from 90, which is 82.3. If we go ahead and compute those, our components end up being minus 35 for the x, and then minus 35 for the y for the wind, and then 30 for the x, and then 222 for the y for the aircraft. When we go ahead and add these for the resultant, we get minus 5 for the x component, and then positive 185 for the y component. The resultant vector is shown here. And again, it makes sense because we have a negative value for the x. That's why it's in the negative x quadrant. Or quadrants, I should say. There's two. And then positive y. That's why it's going in the positive y direction. So again, we're going to replace that vector with this right triangle right here. And this right triangle will represent the vectors, not the distance in this case. So this will be the resultant vector, the original aircraft heading, and then the wind, which is here. Oh, sorry. This is actually the resultant vector breaking into components. So this is the resultant vector. This is the x component, which is minus 5. This is the y component, which is 185. So this triangle represents the components of the resultant vector. And we're going to solve for this new angle, which we're going to call phi, which is this angle right here. And again, this vector has 5 in this direction, 185 in this direction, against the components of the resultant. We're going to use SOHCAHTOA to figure out this phi, and this time we're given the opposite side and the adjacent side. So we're going to use tangent again. Phi equals the tangent inverse of 5 over 185, which is 1.55 degrees. Now we're going to calculate the distance the aircraft has already traveled. And in order to do that, we're going to use the distance and time formula again. And distance equals velocity times time. The velocity in this case is actually the magnitude of the components of the resultant vector. So the velocity is 5 squared plus 185 squared, and then we take the square root. We actually get 185 again. So the velocity is 185 meters per second. When we plug it into this, we'll get distance equals 185 times 3,635, which is the distance the plane has already traveled. Remember, expected arrival time. So that's where we get this value. When we do the calculation, we get the distance is 672 times 10 to the third meters. So if you forget about the components for now, and we pay attention to this yellow dot, which will represent where the aircraft will be at its expected arrival time. So the question is, how far from the destination will the aircraft be? So aircraft is here, and we want to figure out how far it is from the destination if this 50 meters per second wind happens to appear. So now we're going to introduce this new triangle, and this triangle is purely distances. This is the distance we're trying to figure out. This distance is the 800 by 10 to the third meters. That's separating the destination from the starting point. And this is how far the plane has already traveled, which is 672 times 10 to the 3 meters. This is 800 times 10 to the 3 meters. Right now we're going to call this C, which is just an unknown. And we're going to use this alpha, or not alpha, we're going to use this phi, which is 1.55 degrees. Now to solve for this distance, we're going to use the law of cosine. The law of cosine states this. Imagine we have a triangle. We have one side here, A, we have another side here, B, we have another side, C. Then we have these angles, lowercase c, lowercase b, lowercase a. If we're solving for, say, this side, C, which is what we are solving for, we have this relationship. C squared equals a squared plus b squared minus 2 times a times b times the cosine of this angle, lowercase c. So applying that to this, which is what we're trying to solve for, we have this side, and then the unknown, and then we have this angle, phi. Applying the same image into this, and applying the same formula, we end up getting c squared, which is what we're trying to figure out, equals 672 times 10 to the third squared, which is this, plus 800 times 10 to the third squared, which is this, minus 672 times 10 to the third, which is this, times 800 times 10 to the third, which is this, times the cosine of this angle, which is 1.55. When we go and do that calculation, c squared equals 16,777. When we take the square root, we get c equals 130 times 10 to the third meters, or if we divide that by 1,000, we get 130 kilometers. So c, which is the distance the aircraft is from the destination, is 130 meters. Then to answer this question, the aircraft will be 130 kilometers. Sorry, I said 130 meters. So to answer this question, the aircraft will be 130 kilometers away from its destination due to the 50 meters per second wind. Now, stating the whole question all over again, the aircraft should fly on a compass heading of 7.7 degrees east of north, to answer the first part. The flight will take 60.6 minutes when following the 7.7 degrees east of north heading, to answer the second part. And to answer the final part, the aircraft will be 130 kilometers away from its destination due to the 50 meters per second wind. And there you go, we've answered all parts of this question. Good job.